Our universe is filled with compounds. From the chemical composition of a distant asteroid to the salt on your kitchen table, atoms react and bind together in a wide variety of predictable ways. As chemists, we have gradually uncovered these patterns, and then we have needed to develop a language to put those compounds that we have discovered into a kind of order, a framework to categorize our understanding. Welcome to the world of chemical nomenclature. That is the rules of naming compounds. Chemistry divides its world into two great realms. The first, organic compounds, built on chains of carbon, the foundation of life. And the second, inorganic compounds, which are, well, everything else. The naming systems are different, and so in this episode, we're going to step into that second world, where atoms bind together to form salts, minerals, and gases, the substances that shape the earth beneath our feet and the air that we breathe. To name inorganic compounds, we must first recognise a fundamental divide between the elements of the periodic table. To the left lie the metals, atoms that give away their electrons with relative ease to form positive ions, and to the right, the nonmetals, atoms that will receive those electrons or share the ones that they have. This separation is important as it is linked to how the different atoms make their bonds. There will be separate videos on this channel looking at the details of how bonding actually happens. But in simple terms, we can split this bonding into examples of giving and receiving electrons and cases where atoms have to share their electrons instead. When a metal atom donates and a non-metal atom accepts an electron, the result is an ionic compound. So, to make one, we pick one atom from the left of the periodic table and one from the right. As an example, here's sodium and chlorine. Now, I'm going to write their chemical formula down. That is NaCl. When I write that formula, notice that I put the metal symbol first, and when we write its name, the metal is also named first. That element's name doesn't change, and so in this case, it stays as sodium. Now, we write the non-metal's name, and this time it does change, at least a bit. We're going to change the ending to IDE, so that chlorine becomes chloride, and this gives us the very well-known chemical for table salt, sodium chloride. This works for all simple combinations, so MgO is magnesium oxide and KBr is potassium bromide. Of course, not all compounds have this simple 1-to-1 ratio of the elements, and you'll discover the reason for that in my ionic bonding video. But don't worry about remembering the numbers for each element in a compound. You'll actually never have to remember them, because I will teach you how to work them out in the ionic bonding video. So, here's another example, CaCl2. But we follow exactly the same rules. And in this case, it becomes just simply calcium chloride. Al2O3, aluminium oxide. Try this one for yourself. And you've hopefully realised that's sodium oxide. And if you got that one right, you're ready for the next step. If you need a little bit more support, I've produced a worksheet that will give you more practice. And as always, you can ask for help in the comments section below. Before we go any further, I need to introduce a little bit of important language. Remember what I said about metals giving up their electrons? Well, there is a price to pay for that. All atoms start out as neutral, with a balance between their numbers of protons and their numbers of electrons. But if you give some of those electrons away, their negative charge goes with them, and then you're left with an overall positively charged structure behind. We call atoms that have gained a charge ions, and in this case, these positively charged ions are called cations. Similarly, when a non-metal atom takes in an electron, it also gets that excess negative charge, and in this case, we're going to call that an anion. In the heart of the periodic table lie the transition metals, and these play a slightly more complicated game. Where the metals in the first column or group of the periodic table will only lose one electron, and those in the second will only lose two, the transition metals may lose 2, 3, 4, or even more electrons. So while sodium chloride is always NaCl, iron chloride could actually be FeCl2 or FeCl3. And we need to be able to show that when we name them. The modern way to name these compounds requires you to know how many electrons the cation has given away, and then putting that number in Roman numerals after the cation's name and before the anion. In this way, FeCl2 would be referred to as iron 2 chloride and FeCl3 as iron 3 chloride. Depending upon your exam board, you may not come across these at GCSE, but you would certainly need them at A level, so it's good to meet them now and gain some familiarity with the terms. In older textbooks, you might find another way to name these compounds, which actually falls back on a bit of ancient Greek. Using the counting system from that classical period, we have mono or mon for 1, di for 2, tri for 3, and tetra for 4. And we just pop that in front of the anion. So FeCl2 would become iron dichloride, and FeCl3 would become iron trichloride. Now the exam boards won't use that language, but you might encounter it elsewhere, and so I thought it was good to be prepared. You can now accurately name any compound that contains one metallic and one non-metallic element, which is already a huge achievement. However, some ions are not single atoms, but stable groups acting as one. They are called polyatomic ions. And though they may seem more complicated at first, they actually follow a very similar naming system to the one we have just learned. And all we do is cluster those atoms together in a group and name the group. Now there are quite a few of these groups, but the good news is you will only need a very small number of them at GCSE. So if you learn these ones first, CO3, carbonate, SO4, sulfate, NO3, nitrate, and finally OH, hydroxide, that is pretty much all you will need to get through your GCSE course. However, for the more adventurous, here's a longer list, and these are the ones that A-level students can expect to meet during their courses. Okay, here are some simple examples to practice what we've learned so far. Here's a quick one. NaOH, sodium hydroxide, CaCO3, calcium carbonate. Try naming these three compounds. LiOH, NaNO3 and MgSO4. Again, I'll pause the video here and give you a few seconds to work those out for yourselves. As always, there's some more of those examples on the worksheet, and if you get stuck, you can ask questions below. When nonmetals react together, we call this process covalent bonding, and they will share their electrons. This means that they won't form charges, they won't form ions, and therefore we're going to need some new rules in order to be able to name them. The first problem is with two nonmetals, we have to decide which one we're going to put first in the name. And the rule this time is that the element in the lower group number, that means further towards the left-hand side of the periodic table, gets named first. If they're both in the same group, then we start with the one that is closer to the bottom of the periodic table. A bit of higher level language. What we're actually doing here is putting the more electronegative element second in the compound name. Don't worry about that term for now. It is something that will be covered in our covalent bonding video, which I will link below as soon as it's released. But the thing to remember is that chemistry all joins together to make a single picture in the end. And I think it helps to know in advance where those little joins and connections will be made. Now, in order to complete the name, we're going to need those Greek terms again, so that we can distinguish from things like CO and CO2. Now, you probably recognise these ones already as carbon monoxide, 1 oxygen, and carbon dioxide, 2 oxygens. But now, of course, you understand where those names come from. So, let's name some compounds together. Here's SO2, sulfur dioxide, PCl3, phosphorus trichloride, and if you're looking for some more, there's about a dozen of them on the worksheet for you to work through. As always, questions underneath, please. Now, exceptions to these rules. There is one final twist. Of course there was going to be. There are a few chemicals that defy the patterns that we've just been through and have special names. For example, not even a chemist has asked for a glass of dihydrogen monoxide, please. We call it water. Another is NH3, a chemical that plays a vital role in fertilizer production. We simply call that one ammonia. To name a thing is to start to understand it by learning to speak the language of chemistry. And by doing so, we learn to describe the invisible, to give shape to what cannot be seen, and to glimpse perhaps the machinery of our universe. As you use the names of these chemicals, you begin not just to describe chemistry, but to become a chemist. I hope to join you on this journey. If you've got this far, then a huge well done. You can now name pretty much every inorganic compound that you will meet at GCSE in a chemistry course. If you're stuck, watch the video a few times, make sure it sticks in your brain, and use the worksheet to reinforce your learning. You are already well on your way to becoming chemists. And please remember to subscribe to stay updated for the latest content, and drop me a like to know that this was useful to you. I'll see you next time. Take care. Bye-bye.